Hello, what's up guys? This is me again, your resident chemistry tutor Mark, and for this video, we will be discussing about the electric generator and how does it work. So, a brief introduction of an electric generator. As its name implies, it generates electricity, but it does not produce electricity per se, but rather it converts other forms of energy, mainly mechanical, chemical, particularly in the form of the combustion of fuel or fossil fuel, and the most recent among the first two that I've mentioned, nuclear energy, into electrical energy. Now, this is, I believe, the most famous and probably the most revolutionary application of Faraday's electromagnetic induction. Now, the first model of an electric generator was invented by the discoverer of EM induction himself, Michael Faraday. However, his first prototype of an electric generator, which is what we call a Faraday disc, as shown in this picture here, is not that efficient in generating electricity from other means, which is in this case through mechanical means by rotating this crank here. However, this concept found potential among scientists and inventors alike, that they made further improvements on Michael Faraday's first prototype, and subsequent improvements of that prototype later. The electric generator has gone a long way from the normal Faraday disc, the inefficient and rather primitive Faraday disc, into these huge generators that now supply the whole virtually the whole power virtually the whole society. So if we see here that the electrical energy generator is converted from other sources, now powers not only residential but also commercial and industrial sectors. So what are the basic parts of a generator? So a generator is composed of two magnets, wherein the north and the south pole of those separate magnets is flanked by a steel coil, and that steel coil is connected to a shaft, which is also connected to the other source of other form of energy that I mentioned of, may it be mechanical in the form of a shaft or a piston. It's usually a piston, I believe. Anyway, and the other end of the coil is connected to two carbon brushes, which are good conductors of electricity, and those carbon brushes, or rather, they are connected to slip rings, which is in turn, these are the slip rings. If you see it here, this one. These slip rings are also connected to carbon brushes, which is in turn connected to an external circuit. Maybe as simple as a closed circuit of a light bulb, or as complex, for example, a whole household, or rather the whole power grid of a community, which we have seen in the previous slide here. So how does it generate electricity? Now, the shaft that is connected to other external source, may it be a crank or a piston, rotates, and that shaft, which is directly connected to the coil, in turn rotates the coil. Now, since the coil is in between two magnets, thus the magnetic field lines of those magnets, let's say the red part here is the North Pole and this part here is the South Pole, pass through the magnet. That means the coil. That means it passes through the area bound by the coil. Now, rotation of that coil changes the effective area that these magnetic field lines passes through. In turn, produces a change in magnetic flux, and that change in magnetic flux induces a voltage and in turn a current which powers for a circuit, may it be simple, complex, or an entire power grid. Now let us go deeper into the physics of the electric generator. So let us focus ourselves here in our generator coil. So as I've said earlier, that the generator coil is in between the opposite poles of two different magnets. Now if this generator coil rotates at this linear velocity here, if let's say this one side of the coil moves at the same this linear velocity here, and similarly, since this side is connected to this side by this area, by this width of the shaft here, this side also moves at a certain velocity, at the same magnitude of velocity, however in opposite direction, since the coil rotates. Now this is the magnetic field lines, and the velocity, the linear velocity of this length of the coil L moves at an angle theta away from the magnetic field, away from the direction of the magnetic field lines. Now we know from the basics from our in the electromagnetic induction that the induced voltage of the induced voltage of a current, rather the induced voltage of a conductor moving in the presence of a magnetic field is equals to velocity multiplied by the magnetic field multiplied by the length of the conductor, which is, what do you call this, which quote unquote touches or feels the magnetic field. Now we know however, if you remember our example for the electromagnetic induction, so before you proceed to electric generators, you need to view first my video for electromagnetic induction. Anyway, so in our electromagnetic induction, this V here, the only thing considered is the component parallel to the magnetic, perpendicular to, with respect to the magnetic field. And since this velocity is at an angle theta with respect at an angle theta away with respect to the magnetic field lines, that means it will have a component since it is a vector. So this is our theta. So this will be the vector diagram for the linear velocity of the coil. Now our magnetic field lines point in this direction. These are our magnetic field lines. So we have two components here. Let's say this one is VA and this one is VB. Now if you can see, the one perpendicular to the magnetic field lines is the component VB. So from our trigonometric functions, VB is equals to V cosine, or rather V sine theta. Right? Now, since only the perpendicular component is considered for electromagnetic induction, for induced voltage to produce, the induced voltage therefore is equals to VB, B null, magnetic field, B null, times the length of the conductor, or the coil in this case. I hope it's visible. So therefore, we substitute this expression with this one. This will be converted to V B null L sine theta. Okay? So it will look like that. Now let's try viewing the motion, the rotating generator coil at an angle with when we view it here through the shaft. But before that, before I forget, since this one moves and this one also, since this one moves and this one also, this side of the coil here moves at this direction at the magnitude v, and this one moves at the opposite direction at the same magnitude of velocity. Therefore, this length of conductor produces an induced voltage, and this one and this opposite length of the coil also produces an induced voltage of the same magnitude as the other side. So that means the total induced voltage produced by the generator coil is equals to the sum of the induced voltages that each of these sides of the generator coil produce. Since parehas man lang sila magnitude, so we just multiply this by 2. So this will become 2b null L sine theta. Now if, okay, I need another whiteboard. I hope it's visible to you guys. Yeah, that's it. Perfect. Now if the coil is wound, not wound that is an abrasion, an abrasion of the flesh, but rather a wound that is a past tense of wine. Is wounds n times. So that makes the induced voltage, the total induced voltage, into, we multiply this by the how many times, the original expression, which is this one, we multiply this by how many times the generator coil was wound. 2n v b now L sine theta. Now now we look again. We look at the generator, the motion of the generator coil through the shaft. So let's say we look through here. I hope you can see. Look through here, and our view will be like this. So this is our shaft. And this is the width of the coil, which is, we will denote as W. It's the width of the coil, and since the coil rotates, it traces a circular path, right? Now, the V that we have described a while ago is just actually the tangential velocity. Okay, since this is now a rotational motion, that means it will now have an angular velocity of omega. And we know from our rotational mechanics that omega is equals to theta over t, or is equals to linear velocity divided by r. Now, again, for angular velocity, the theta here will be in radians, okay? So when you compute for your angular velocity, don't forget to convert your angles into radians first before solving for the angular velocity, okay? That is one of the common mistakes that physics students like you and me once did. Me once usually do. Well, before I sometimes make mistakes that I forget to convert my angle into radians when solving for angular velocity. Okay, so do not do the same mistake as I did when I was a student. Okay. Anyway, so, and we know And as we have seen here, since this traces a circular path, so we'll just draw here a circle. Now the width of the coil is actually the diameter of the circular path that it traces. And since diameter is equals to twice the radius, so therefore our radius is equals to half of the width of the coil. And that will be, and that will change your angular velocity into okay, it's hanging again. I'll fix this, guys. Okay, I'll be right back. Okay, going back. The angular velocity will be, what do you call this? The angular velocity, therefore, will now be equal to V over W over 2, or 2V, 2 times the linear velocity multiplied by the width. Okay. Also, in terms of the angle over time, also from the angular velocity, theta, or the angle of motion, is equals to omega times time. Okay. Now we substitute the wait, not yet. So from here we get the velocity. So velocity here is equals to double omega times W over 2. Now we substitute these values to our original equation here. If you can see, we substitute these two to the ones here and here. Okay, so our resulting equation will now be will now be 2n omega W over 2 multiplied by B null L sine omega times time. Okay? Don't go away, guys. I'll get another whiteboard. And since there's 2 in the numerator and 2 in the denominator side, they cancel each other out. And another thing, since this one is multiplied to this one, to the length of the coil, so we know that length times width is equal to the area of the coil. So we substitute this expression to the formula of the induced voltage of the generator coil. This will now result in 2 n B null A, n omega, B null A omega, I forgot the angular velocity, multiplied to sine omega over time. Okay. Now, in order to complete one full rotation, ouch. In order for the when the coil makes one full rotation, theta will now therefore be 2 pi, right? Thus, from the formula of angular velocity, which is theta over time, so angular velocity is 2 pi over t. Okay. Now, if you're familiar with the concept of frequency, now frequency is the time it would take. The frequency is the number of cycles or number of what's another term for cycles? Maybe The cycle may be, for example, a complete revolution, a complete rotation, or a complete motion, for a complete back and forth motion. Well, in the terms of physics, the frequency is equal to the number, to how many times you perform one complete task. Yeah, that's it. One complete task at the number of times you perform complete task at a given amount of time. So usually, frequency is denoted as the amount of complete tasks that you can finish, let's say, in 1 second, or 1 minute, or 1 hour. Okay? So the unit for frequency is usually 1 over T, or this is in SI unit our hertz. Okay? So frequency is equals to 1 over T. Therefore, our angular velocity can be expressed into 2 pi, instead of 2 pi over T, you can express in terms of frequency, which is 2 pi times F. Okay? So this is the end of our really short video for AC generator. So again, I hope you find this video educational. Don't rely on my videos alone. Read more and more references in order to gain better, if not deeper, understanding of the topic. Okay, so that's it. See you.